Okay, thanks. Hi, everyone. I'm Yihan, a postdoc from UNLV. So I'm going to talk about this enhanced TD rating agent. Indeed, this project inspired by one of my another project about the black hole merging agent disks. So basically, but after that, I found that this dynamics can also be applied to TDEs. So people find that like the binary fraction in the Euclid cluster is relatively low. The reason is that the velocity dispersion in such an environment is very high. So the binary evaporation due to scattering is very fast in this environment. So it is very hard to find binary in the nuclear cluster. So some people come up with this very fancy agent information channel to try to explain the black hole mergers. And we get like a accretion disk here to settle down the black hole in the accretion disk. Then it's much easier to form a binary in this system. And I found out this the process is very can be also applied to this tidal disruption event in nuclear cluster. So here is basically a very simple picture about the nuclear star cluster. Unlike the quarks and galaxies, we get accretion disk in the region 3, and the dynamics of this system will be characterized by three radii. The first is the tidal disruption radius. I don't think I need to explain what is this in this conference. And the second is basically self-gravitating radius of this accretion disk. And beyond this point, the self-gravity of the accretion disk becomes more important than the gravity from the supermassive black hole. So the accretion disk will basically collapse. And this can be regarded as basically the size of accretion disk. And the third one is basically the size of the nuclear cluster RC. And by these three radii, this nuclear cluster can be divided into 4 regions. So the first region is the region 1, where the stellar orbit in this region will barely interact with the accretion disk. So the dynamics is dominated by the relaxation process. And the region 2, we have a lot of like off-disk orbital around the supermassive black hole. And in this region, the stellar orbit will interact with the accretion disk. And in the region 3, we get a bunch of stars fully embedded in the accretion disk. And the dynamics of this would be completely different from the region 2. And the most important region is in region 4 I'm going to talk about today. I will tell you that in this region, a lot of stars will be delivered to the vicinity of the supermassive black hole with a very short time scale. So I will go through like these 4 regions one by one. The first region is region 1. We have like a relaxation process. So basically in the nuclear star cluster, we have a lot of stars orbiting around the supermassive black hole. And this orbit can be described basically by the specific binding energy and angular momentum of this orbit. And due to the gravitational perturbation from other stars, basically those orbital will perturb. And this energy and the angular momentum of this orbital will basically fluctuate with the so-called relaxation time scale. And if we consider the TD process, I think it is better to say this this relaxation process in the energy and angular momentum parameter space. And if we plot this orbit in the energy angular momentum parameter space, we will find that there is an upper limit of the angular momentum for a given and specific orbital energy. This corresponds to the circular orbit for this given energy. And if we check like some states in this parameter space, like the blood dots, low energy and high angular momentum, this corresponds to a weakly bound orbit, nearly circular orbit. And if we check like an orbit here, like the low binding energy and the low angular momentum, it corresponds to like a high eccentric orbit, weakly bound. And there are some other orbits, like some like here, like a very high binding energy and low angular momentum. This corresponds to a very close orbit around the supermassive black hole. And if we consider the relaxation process, for example, if we have like an orbit at very low energy and high angular momentum region, due to this relaxation process, this orbital will stochastically move in this parameter space. And since this binding energy in this region is very low, so this stellar orbiter will move slowly horizontally. However, this maximum angular momentum in this region is very high. So basically, you will move fast vertically. And if we consider a stellar orbit like in the high binding energy region, and due to this relaxation description, you will find that this stellar orbiter will move fast horizontally, but it's difficult to move vertically in this region. And And here is a very special, like angular momentum corresponds to a tidal disruption event, radius. We call it like a loss cone. So any stellar orbit stochastically enter into this loss cone will trigger a TD at the period center. And of course, we have like event horizon of the supermassive black hole. If the period center go deeper into this region, you will not detect a tidal disruption anymore. And basically, if you want to calculate the tidal disruption rate in a quiescent nuclear galaxies, basically you just estimate the mass flux at the boundary of the loss cone, and you adopt a third-cluster model that will determine how the stellar orbital will populate in this parameter space. And in the low energy region, you will find that the angular momentum fluctuation is much larger than the loss cone size. So any state within the loss cone consumed by the supermassive black hole will be quickly refueled by the stochastic motion from the relaxation process. However, in this high energy binding energy region, you'll find that the angular momentum fluctuation is much smaller than the loss cone size. So all the stars disrupted in this region, they cannot be refueled by relaxation very fast. And this is a typical size to discriminate the full loss cone and empty loss cone region is roughly parsec size, and you can also change the mass of the supermassive black hole. If your mass of the supermassive goes faster, your loss cone size becomes larger, and of course your event horizon will go up as well. However, this loss cone size increases slower. It is proportional to 1/3 of the mass of supermassive black hole, and your event horizon goes faster. It is linear to the mass of supermassive black hole. So you will see that your loss cone region will decrease as the mass of the supermassive will go up. So you will expect that the TD rate becomes lower and lower as your mass of supermassive goes higher and higher. And this is the region 1, and the region 2 is the more interesting region where the stellar orbit will interact with the accretion disk. So here we have accretion disk. This is the angular momentum of the accretion disk, and this is specific. This is the scale height of the disk. This is a very simple disk model. You can adopt a more complicated one. And this is a disk velocity in this direction. Now here comes like an orbit of disk orbit with some inclination with respect to the accretion disk, and this is the angular momentum of this orbiter. So for each period, the object passes through the accretion disk, it will feel like a drag. And the drag is like in the opposite direction of relative velocity between the two velocity vectors here. So if we assume that the disk is not strongly turbulent, then we can assume that the disk velocity is basically the local Keplerian velocity, which is equal to the orbital velocity of the orbiter. And your relative velocity is basically can be described like with the Keplerian velocity times the 1 minus the inclination. If the inclination is 0, basically you don't have any relative velocity. And if it is purely retrograde, it is twice of the velocity, Keplerian velocity. And this is the torque you will feel. And if you calculate the torque of this force, it is basically on this direction. So the picture is that this angular momentum is in this direction, and you will feel a torque once you pass through accretion disk. And this torque will gradually align the angular momentum of this orbit to make this object to be captured by the accretion disk. And indeed, there are two forces in this drag. The first is the aerodynamic drag. It's basically a ram pressure deceleration, which is proportional to the geometric cross-section of this object, and the density of the median and the square of relative velocity. And this is like a coefficient in front of it, described like, basically used to describe the, it's determined by the shape of this object. For most of the astrophysical object is a sphere or disk. This parameter is very simple. And if you consider like a very complicated engineer problem like the aircraft, this parameter can be very complicated. And the second drag force is the dynamic friction. This is a purely gravity effect. So if you have an object moving in a median, and this object will like exert the gravity on the median behind it and form like a very dense region. And this dense region will pull back this object to exert like a dynamic friction force on it. This is inversely proportional to the square of the relative velocity. However, if we can rewrite this formula in this way, then you will find this boundary Hoyle radius. And if you compare this boundary Hoyle radius with this geometry size of the object, if this geometry size, cross-section is larger than the boundary Hoyle cross-section, then your aerodynamic drag dominates over the dynamic friction process. However, if your boundary Hoyle radius is larger than the size of this object, then your dynamic friction dominates over the aerodynamic drag. And here I show like some example of this geometry size of the object and the boundary Hoyle accretion radius around the 10 to 7 solar mass supermassive particle at 1000 Rg. And there are some like main sequence star here and compact object. You can see that, of course, this depends on the relative velocity, that depends on the inclination. And shown here, this is purely retrograde, or this is purely prograde. So you can see that for main sequence stars here, no matter what is the inclination, the geometry cross-section is always larger than boundary Hoyle cross-section. And for compact object, you can see that this boundary Hoyle radius is much larger than this geometry size of this object. So because here I talk about TD, so we focus on the stars. So for the stars, basically all the orbiters, if these stars, their aerodynamic drag will dominate over the dynamic friction in this process. And if we write down the equation of motion of this disk orbital process, you will find that this is proportional to the ratio of the disk surface density over the surface density of the star. And here I only show a very simple case where the orbiter is in circular orbit. In reality, it is more complicated. This equation of motion should be also a function of the eccentricity and the argument period absence of this orbit. But no matter what is the eccentricity and the inclination of this orbit, you will find that this three equation like always negative, which means that this process will always shrink the orbit, damp the eccentricity, and align this or this orbit on this time scale. And this is basically the picture for this. We have a lot of stars orbiting around the supermassive particle interact with the accretion disk, and your low inclination orbit will capture by the disk at a very large radius, and your high inclination orbit will capture with the inner radius of the accretion disk. And if you compare this time scale with the relaxation time scale, you will find that in the inner region of the accretion disk, this time scale is much shorter than this. So the dynamics in the region 2 is basically dominated by the disk-star interaction rather than the relaxation process. And here I adopt like a Shakra-Sunyaev disk in the inner region, and the surface density is not real. It's very, very high. So because in this solution, they didn't consider like a radiation pressure, but in reality, this time scale will flat out here. And this is very interesting in this process is I found that this integral motion in this dynamic process is basically a combination of the angular momentum and the inclination. We can rewrite it in this way. Basically, it's the average between the angular momentum and the angular momentum in the z direction. And this is it's easy to understand. So this is our disk-star interaction, and we have angular momentum in this direction, and we have a torque in this direction. And this is the z component of the angular momentum, and this is the integral motion that it is constant during the star disk interaction. And you will find that this is nearly perpendicular to the torque. So the picture is that this torque will gradually decay the parallel component of the angular momentum, but rotate the perpendicular component of this orbit. So this quantity is almost constant during the disk-star interactions. And although this is not like a rigorous integral motion that can be derived analytically, but we found that this is a very good, we use the numerical simulation to verify this integral motion. We find that this is a very good approximation. And this has a very important implication. So if we plot this integral motion in this inclination angular momentum plot, you will find that the orbital evolution basically follows this contour lines. And if you have like a very highly inclined retrograde orbit, you will find that the angular momentum will be decreased by several orders of magnitude during the disk-star interactions. And so this would be a very important source for the tidal disruption event. So we have like for those orbits that's nearly retrograde with 180 degrees, since due to this integral of motion, the angular momentum will be decreased by several orders of magnitude. And if this final capture radius is within tidal disruption radius, then those stars will be captured within a tidal disruption event to trigger potentially trigger tidal disruption event. Although the formology of the tidal disruption agent will be different, I will talk about later. And if you check the time scale for this region, you will find that due to this sign I here, this decay would be very, very fast. Next, I will talk about the region 3, basically the fully embedded orbit. Basically, the fully embedded orbit can also be divided in two subgroups. The first subgroup is the retrograde, the fully embedded retrograde within the agent disk. So this dynamics is very similar to the region 4. And for this case, if this orbiter is off disk, for each period, this orbiter will interact with the accretion disk twice. And the interacting pace is basically roughly the scale height of the disk. However, if this orbiter becomes fully embedded, then you will interact with the disk for the full period. So your dynamical equation of motion can be just modified by applying this interaction pace ratio between the fully embedded case and this orbital off-orbital case. You will find that the time scale will be shortened by a factor of the aspect ratio of accretion disk. So the fully retrograde embedded disk, they will be damped their semi-image axis, eccentricity, and inclination is not important because it is already fully embedded. Much faster, and if you compare the time scale with this fully embedded in region 3, and it would be much shorter than the disk capture time scale. And another group subgroup of the fully embedded is like a prograde. The prograde, since the relative velocity between the orbit and the disk is nearly 0, so there's no aerodynamic drag and dynamic friction. And instead, we have like a dynamics like this. This is a well-studied problem in protoplanet disk community. And depends on the mass of the orbiters, the dynamics will be slightly different. If your Higgs radius of the small orbiter is smaller than the disk scale height, then about the scale height of accretion disk, the dynamic is dominated by the gravity of the supermassive black hole. Then your small object cannot open a gap in your accretion disk. Then your orbiter will migrate within the disk due to this Lindblad resonance. The Lindblad resonance, basically this embedded object will exert a density within the accretion disk, and this density will exert a torque on those objects and make them migrate within the disk. And if your Higgs radius is larger than the disk scale height, then at the disk scale height, your gravity from the small object is more important. Then you will open a gap in the accretion disk, and your migration time scale is basically determined by the viscous time scale. And if you compare this resonance time scale with some other problem, you will find that this time scale for the Lindblad resonance is much longer than aerodynamic drag. So basically, the big picture is that the star will be constantly captured from the nuclear cluster from region 3, and they will be captured in the disk, then will gradually migrate within the disk with a much longer time scale. So here is the whole picture of the TDE in the AGN phase. So the first, when the disk formed, you get like initially fully retrograde orbit. This initially fully retrograde orbit will be transferred to the vicinity of the supermassive black hole within very, very short time scale. And then for those orbiters that are slightly above accretion disk retrogradely, they will be also be tidally discaptured, or not tidally, but will be captured with a tidal radius around the supermassive black hole with a very short time scale. And this happens only at the early stage when the accretion disk formed. And this process is non-renewable because those retrograde orbiters cannot be refueled by any disk-star interaction, because the disk-star interaction tend to align all these orbiters. And the relaxation process timescale is too long to refuel a star in this region. And once the accretion disk formed, then we have a steady in-disk TDE from prograde orbit from the Lindblad resonance migrate on this time scale. And And the disk will constantly capture star from this region 2 and or in progress orbit refill this. And this process will be provide like an enhanced TD rate in the AGN phase. And of course, we have like background relaxation process in the region 3 that provide like a lower floor for this. And if you compare the time scale of the floor, you can find that the initially full retrograde migrate faster than this region 4, and smaller than the capture process, and smaller than the Lindblad resonance, and smaller than the relaxation process. And there's a very interesting feature for this TD related to the disk. If this TD related to the disk process, they will tend to have like a very low eccentricity as they approach the tidal disruption radius of the supermassive black hole, because this disk star interaction will damp the eccentricity. And however, the relaxation process tends to produce a very high eccentricity. So those stars, as they approach the supermassive black hole, this highly elliptical orbit, and this will give different like TD morphology in the accretion. Then we can like play with this model by adopting different disk model like Shakran-Sunyaev, like Shakran-Goodman, and Thompson. And this is basically surface density profile. If I calculate the TD rate in this AGN phase, basically two different disk models. And this is the AGN lifespan. We have a relaxation TD background from region 1, region 2 is here. And we have like an in-disk tidal disruption event basically shows this dotted line. There's a spike, like a very high TD rate in the very early stage, but gradually decay. Then we have like a capture TD rate as most important TD source in this AGN diagram. From the region 4, they provide a much higher TD rate based on this above this relaxation TD process. And there are some like I would say like the TD morphology would be different in AGN case rather than quarks and galaxies. There are some simulations show the off-disk TDE, like their string will collide with the accretion disk, and also one of my collaborators performed some simulation about the in-disk TDE. Probably I don't have time to go through this, but I would like to say that the TD agent risk can be well connected to the change rate agent, because this in-disk TD will significantly change the accretion rate of the accretion disk. And the TD is very problematic to explain the change rate agent in the past, because we find a lot of change rate agent when supermassive black is much larger than the truncation mass, and the TD rate is too low. However, if we introduce this AGN TD, I will find that this can be well explained. And I think I don't have time to go through all this still, but here are some takeaways. Basically, the AGN disk can quickly transport a substantial amount of mass to the vicinity of the supermassive black hole during in the early AGN phase, potentially will cause the TD outburst. And those stars arrive with relatively low eccentricity, different from the star diverted by the relaxation process. And the TD in AGN and probably hard to detect or identify, but it's highly possible to alter the accretion disk state, probably leading to a change in local agent state. And here is my relevant paper, and you can scan the QR code. I'm happy to take any questions. Thanks.
Questions? Maybe I'll start. Have you looked into the effect of the passages of the stars through the disk on the stars themselves? Could they be partially stripped or ablated?
Yeah. For this, if it is like off disk, for this case, if it's off disk, I think the RAM pressure stripping is not very important. However, if there's an in disk tidal disruption event, when the star approaches the tidal disruption event, the RAM pressure stripping can be important. We haven't, because this model we just it's a rate calculation, so we haven't explored the details of this disruption event. But I would like to say that this will be very different from the TD in quarks and galaxies, especially this in-disk tidal disruption. There will be RAM pressure stripping about that. Also, the tidal heating, that will change the dynamics a little bit. Yeah, sure.
Let's start with that side.
Thanks, this is really cool work. Maybe it's related to what's up here, but can you give me a sense of how this picture would change rather than like a radiatively efficient AGN? You have maybe a low luminous AGN, different disk structure?
Sorry, I cannot answer that because I'm not very familiar with that part. But because we are still investigating like what is the in-disk TDE for morphology of the in-disk TDE. And one of my collaborators performed this simulation, but before I told him what is the correct configuration parameter should be used in the accretion disk. So we are still investigating how this will change like the process, like what is the energy release from this process and how that will change the luminosity of the agent design. I don't have a good answer at this moment, sorry.
Ryan?
So on small scales, the Thomson quadrant-Murray model reverts back to Shakur's and Yaya, but
yeah.
Here they're like the orders of magnitude different. So how are you normalizing these models to each other? Are they the same accretion rate onto the black hole, or the same feeding rate from the outside, or how are you sort of comparing apples to apples?
What do you mean? Like, because this model adopted from the paper. This is, if I remember correctly, this profile for Thomson is from 10 to the 9 supermassive black hole, and the super good band is from 10 to the 8 supermassive.
So you just took the models from their paper. You're not trying to compare like the same black hole accreting at the same rate with these different models.
Yeah. We basically adopt what the disk parameter in their paper. We didn't like compare like different disk models.
Yeah, maybe interesting to try to normalize the same, say, black hole accretion rate.
Yeah.
Another question is, I think you addressed this, but so how much is in a given epoch of time over this whole AGN phase? How much is the black hole growing from gas accretion versus these enhanced TDEs? You were saying at one point that you think this sizable fraction of the growth can come from the TDEs.
Yeah, let's think about it. If it is like a 10 to the 8 supermassive, 10 to 8 is too stream. 10 to the 7 supermassive, solar mass supermassive, the accretion rate, if we assume it's Addington, is 0.1 solar mass per year. So it's here. And so for this enhanced TD rate, this is probably just comparable to the accretion rate from the accretion disk. Yeah. If it goes slower, I didn't show like a 10 to a 6 case. Then the Addington accretion rate is 10 to -2, and this plot, if I remember correctly, will be slightly slower as well. So basically, with this boosted tidal disruption event, the fading rate would be comparable to the accretion disk.
So I would say that when we're seeing an AGN integrating over its a bit like we're just as likely to see a TDE at any given time than just steady accretion.
Yeah, maybe.
Short?
Yeah, I don't think that is
Like this? Yes.
Yeah, sure.
Yeah, thanks. I have a naive question and then an encouraging remark. So I was thinking for the sun we have this magnetosphere which deflects all the charged particles. So would that affect the aerodynamic drag that you calculate, or this would be much bigger than this?
Yes. Yeah. So here, I think that basically we are talking about the linear coefficient in front of it. I think that will significantly affect this linear factor. I don't know by how much. Probably within 1 order of magnitude. I have no
I guess it depends if it's neutral or ionized, I guess.
Yeah, that's true. Yeah, but here we assume that this parameter is roughly 1. So the calculation, if the parameter is much smaller than that, the aerodynamic is weaker. But I don't know by how much. Probably within order of magnitude.
Thanks. Yeah. And then at the end, you compare to the mass distribution of these changing look AGN, and that it's above the Hill's mass, which would, which maybe we can fix, but maybe it doesn't even need to be fixed. This is my encouraging remark, because I think the changing look AGN, it's a spectral state change of the AGN, but what you care about is a large flux increase. So it could be a type 1 AGN that stays a type 1 AGN, it just has a large outburst. So it's more related to these ambiguous nuclear transients or Bowen line flares that we see. So and we don't know exactly what mass distribution they follow, and they probably peak more below the Hill's mass. So then it may actually work out much better even than here.
Yeah, that's true. Yeah, I think the problem for relaxation TD is that if you even make the supermassive faster spin, you cannot go much further. However, for this, our disk model, if we adopt like an initial mass function, we have very massive stars. Then, because this capture process will very efficient to transport the massive star to the vicinity of the supermassive black hole, so you can go much further than that. Yes, basically this is my summary intuition.
Okay, so let's thank Yihan once again.